We're continuing our discussion of the fundamental theorem of algebra. This is part 2. And what I want to talk about first here is what's known as the complex conjugate pairs theorem. It says that if we have a polynomial and it has real coefficients, that means all the coefficients are real numbers. And for us, that's no big deal because we don't generally look at polynomials that have imaginary numbers as coefficients. Then if a plus bi is a 0, that is where it does have some imaginary part to it, then its complex conjugate is also a 0. So what we're saying is if we had some polynomial that has real coefficients, if something like, say, 2 plus I was a 0, then that would tell us that 2 minus I is also a 0. So we kind of get a 2-for-1 deal. If we had something like, say, I square root of 5 as a 0, then its complex conjugate, negative I square root of 5, would also be a 0. Now, we can extend this idea, the complex conjugate pairs theorem, to go beyond just complex numbers. If I change the condition, instead of saying real number coefficients, if I said something like all the coefficients were rational numbers, or what we'll see oftentimes is integer coefficients, then what that would mean is not only can we get pairs besides imaginaries, but even if we had something like, say, 2 plus the square root of 5. In this case, the square root of 5 is irrational. So if our coefficients are rational, and integers mean that they have to be rational as well, then that would imply that there would be another 0 that would be not the complex conjugate, but what we just call as the conjugate of that, something that would make it be the difference of two squares. So for example, if we said something like 1 minus the square root of 2 was a 0, and we had integer coefficients, that would mean that 1 plus square root of 2 is also a 0. So let's see how this is going to work out. Let's build a polynomial. Here's our first example, and we want a 4th degree polynomial, and we're only told 3 zeros. And we know that a 4th degree polynomial from the fundamental theorem of algebra must have 4 zeros. But because of our new theorem, the complex conjugate pairs theorem, if 3i is a 0, then negative 3i must also be a 0. So then, given that, we can now build up our polynomial. If 1 is a 0, x minus 1 is a factor. If negative 1 is a 0, x plus 1 is a factor. If 3i is a 0, x minus 3i is a factor. And if negative 3i is a 0, x plus 3i is a factor as well. So we're going to want to multiply this all out. So it doesn't matter the order we do it in, but I think it's going to be a little bit easier if we kind of group these together, because we got a couple of nice difference of two squares here. So if we multiply the first two out, x minus 1, x plus 1, we're going to get the difference of two squares, x squared minus 1. If we multiply x minus 3i times x plus 3i, we're going to get x squared minus a 9i squared, which is going to become, because I squared is negative 1, that's going to become an x squared plus 9. And then we can finally multiply that out, and we'll get an x to the 4th, the 9x squared, and a minus x squared, and finally a minus 9. And so our polynomial is going to be x to the 4th plus 8x squared minus 9. There is our 4th degree polynomial that has zeros 1, negative 1, 3i, and then by default it must also have negative 3i as a 0 as well. So let's look at another example. I'm going to go to the next page, which I've already written down the problem. So let's find a polynomial with integer coefficients and zeros 2/3 and 1 plus 2i. So we know from our complex conjugate pairs theorem that our polynomial is going to also have to have 1 minus 2i as a 0. Now we want factors, so we know that x minus 2/3 would be a factor, but since we want integer coefficients, we want to clean this up and make it something that is not going to give us fractions. So if we multiply through by 3, that's going to give us 3x minus 2 as a factor. So we're going to get 3x minus 2 times. Now from the 1 plus 2i, we're going to get x minus 1 plus 2i is going to be a factor, which when we distribute that is going to give us a factor x minus 1 minus 2i, x minus 1 minus 2i. From the factor 1 minus 2i, we're going to get x minus 1 minus 2i will be 0, so that means our factor is going to be an x minus 1 plus 2i. So there is our factorization, but now we want to multiply that all out. We talked about this before a little bit. On this second pair, we can make this more efficient if we insert parentheses around the x minus 1's and then recognize that as the difference of two squares. There's an a minus b times a plus b. So if I'm going to multiply those together first, so that is going to give us an a squared, which is going to be x minus 1 squared, minus b squared, and 2i times 2i is going to be 4i squared. So this, we're going to still hold off on the 3x minus 2, but now I'm going to square out the x minus 1, first one squared, twice the product, plus the second one squared. A minus 4i squared is going to become a plus 4 because I squared is negative 1. And so then, at long last, I'm going to kind of brute force this binomial times a trinomial. I don't have a great way of doing this. When we multiply by 3x, we'll get 3x cubed minus 6x squared minus 10x. And then I'm going to come back with the negative 2. That'll be a negative 2x squared plus 4x and a minus 10. I try to write those where like terms line up underneath each other. So we're going to get then 3x cubed minus 8x squared. And let's see, what was that number I wrote? I guess that's a negative 10x plus 4x is a minus 6x minus 10. There is our polynomial with integer coefficients, and it has the zeros that we wanted. Okay? Very good. Let's try one that's a little different style. So in this case, I'm going to say find the zeros and factors. Find the zeros and factors of, and I'm going to tell us that our polynomial to start with is p of x is x to the 4th minus 3x to the 3rd plus 6x squared plus 2x minus 60. And we're going to be told that 1 plus 3i is a 0. So this is good news. So if we know that 1 plus 3i is a 0, then from our complex conjugate pairs theorem, we know that its conjugate, 1 minus 3i, is also a 0. Now, if we have two zeros, then we have two factors. So what I'm going to do is, we have an option. We could put 1 plus 3i in the box and do synthetic division, but that's going to be a lot of work using imaginaries. Then we would take that result and then put 1 minus 3i in the box and do synthetic division a second time. Now here's what I think is a little more efficient way. If 1 plus 3i is a 0, x minus that, which is x minus 1 minus 3i, times x minus 1 plus 3i, the factor I get from that second 0. This is a factor as well. If each of those individually is a factor, then their product is a factor. So I'm going to multiply those out using that strategy that we keep coming back to of inserting parentheses and calling it the difference of two squares. And again, we're going to get the a squared, which is x minus 1 squared, minus the b squared, which is a 9i squared. I'm going to multiply out the x minus 1 squared. That's x squared minus 2x plus 1 minus 9i squared is a plus 9. And so that is going to be x squared minus 2x plus 10. Now, instead of doing the synthetic division twice, what I'm going to do is long division once with this quadratic. So I'm going to divide this x squared minus 2x plus 10 into our original p of x. X to the fourth minus 3x to the third plus 6x squared plus 2x minus 60. Now, if I do this right, and these are in fact zeros, I should get 0 for a remainder. So I'm going to say what times x squared is x to the fourth. That's going to be an x squared. I'm going to take x squared times the x squared minus 2x plus 10. That's going to give me, I'm going to change colors here. It's going to give me x to the fourth. That's going to be a minus 2x to the third and a plus 10x squared. I'm going to subtract that quantity. And when I do that, the x to the fourth minus x to the fourth drops out. Negative 3x cubed minus a negative 2 makes plus 2x cubed is a negative x cubed. 6x squared minus 10x squared is a negative 4x squared. I'm going to bring down the plus 2x and the minus 60, and we'll repeat the process. What times x squared will be a negative x cubed. So that's going to be a negative x. So negative x times x squared is, I'm going to change color again. Let's go with a negative x cubed. Negative x times negative 2x is a plus 2x squared. Negative x times 10 is a negative 10x. And I'm going to subtract that quantity. So that's going to take us to the x cubes drop out. Negative 4x squared minus the 2x squared is a negative 6x squared. 2x minus negative 10 makes plus 10 is a plus 12x. Negative 60 minus 0 is a negative 60. And we're going to repeat this process again. So now we're saying what times x squared is a negative 6x squared. That's going to be a negative 6. So let's see, changing color again. I'm going to go back to green. Negative 6 times x squared is negative 6x squared. Negative 6 times negative 2 is a positive 12x. And negative 6 times 10 is a negative 60. This is good news because we said we should get a remainder of 0, and in fact we do. So what we now have learned is that our polynomial, this x to the fourth minus 3x cubed blah blah blah, can be written as, it can be factored into, we've got x squared minus 2x plus 10 that we divided by, and we've got that quotient up above, which is x squared minus x minus 6. We can now factor this completely. We know that the x squared minus 2x plus 10 came from these factors up here. So I'm going to, let me go back to the white. So I'm going to call that x, excuse me, x minus 1 minus 3i, and x minus 1 plus 3i. We can factor the x squared minus x minus 6 without too much trouble using our box and diamond, or recognizing that's going to be an x minus 3 and an x plus 2. So here is the factorization. I'm just going to say that is our p of x. That's our factorization there. And we can say that our zeros are going to be the 1 plus 3i we were given, the 1 minus 3i that we got from the complex conjugate pairs theorem, and now the 3 and the negative 2 that we got from our factorization. Very good. Hope that's some help.